Hi guys, this is Dr. Momsilovich with your lecture 11.1 on population growth models. When we're looking at population growth, we can determine the future population size for any population by looking at the current population size plus the number of births in that population minus the number of deaths. So in this case, we're assuming that there is no immigration or emigration into that population. So we can use a really simple equation where the change in the population over time is equal to the rate of change times the population size. We use letter capital N to denote the current population size, and we use letter little r to represent the number of births minus the number of deaths. So if you look at the equation where it says dn over dt is equal to r times n, we're saying that the change in the population size over time is equal to the rate of change, which is the number of births minus the number of deaths, times the current population size. So as we're going through these equations, if this is a little bit confusing and you're having a little bit of difficulty understanding this, if you go to the lecture slides that are posted online, in the notes below the slides, there are links to the Khan Academy, which has detailed videos of how to solve these equations. And so sometimes it's easier to have someone else explain the same thing to you in different words and with a little bit more visuals that might help you out with learning some of this. So within population growth, there are two basic models for the way that a population can change. The first one is exponential growth, and this is where the per capita growth rate, or little r, doesn't change even if the population gets very large. So your change in the population over time is the maximum rate of change times the population size. And if we look at it graphically, it looks like a J-shaped curve. And essentially it happens that way because with this equation, you're adding more and more individuals depending on how large your population size is. So if you have more individuals, the rate is increasing even faster. And so you have a faster and faster increasing population, and you end up with a J-shaped curve. The other type of population growth model is called a logistic growth model. And this is where the per capita growth rate, or little r, gets smaller as the population approaches its maximum size. So in this model, we add in a variable that's called k. And k is called it represents the carrying capacity, which is the maximum number of individuals of a population that the environment can support. And this type of growth ends up looking like an S-shaped curve, where as the population size gets larger and approaches that carrying capacity, the rate of increase will slow down because you're no longer going to be able to add more individuals to that population because there are no longer enough resources to allow more population growth. So if we start with the simpler version, or the simpler equation for population growth, which is exponential growth, you can see that the change in the number of individuals in your population grows faster the larger your population size gets. So if you look at the bottom right hand corner of your screen, a lot of the time we see this happening in like bacterial cultures and things like that. So if you start with one cell, it can divide, and the next day you have 2 cells. The next day, after they've divided again, you have 4, and then 8, and then 16, and then 32, and then 64. So that the larger the population size gets, the faster the rate of increase, because you have more individuals to contribute to the next generation and therefore your future population size. So your rate of increase goes faster the more individuals you have in your population. For exponential population growth, there is a linked Google Sheet on the slides. If you go back into the slides that you can view on Canvas, and you can actually play with the numbers, and you can play with the number of individuals at the beginning of the population and the rate of increase and things like that. And you can look at how that affects the population growth rate for a population. So I do encourage you to go and do this so that you can sort of see how different factors can affect population growth. This is kind of a good lead into something we're going to do later in the semester, where you're going to do a little bit of modeling of different parameters and looking at how different things affect different variables. So definitely go back into the slides and go play with this a little bit and see how different things can affect your population size. The other type of population growth that we see is called logistic growth. And in logistic growth, there are limiting factors that make it so that a population cannot just grow infinitely forever. And so your R value will not stay the same. It will change as you run out of resources. Limiting factors in an environment could be the amount of food or the amount of nest spaces. It could also be diseases, which are easier to spread between individuals in a dense population rather than a more spread out population. And so the limiting factors can either cause fewer births or more deaths, depending on what that limiting factor is. And those limiting factors determine the carrying capacity of that environment, which is just the maximum number of individuals that the particular environment can support. So in logistic growth, you'll initially have a very rapid increase in the number of individuals, but as you reach that carrying capacity, the rate of increase will slow down so that you don't overshoot your carrying capacity and you don't end up with too many individuals for that environment. So let's look at an example of this. So if we have a population with 50 individuals and the carrying capacity is 150, if we do the equation and look at the math, when we have a carrying capacity of 150 and we only have 50 individuals, when we divide that 150 minus 50 divided by 50, you get 2. So we have far more space in our carrying capacity left, and therefore we are adding more and more individuals to that population. So our rate of increase is still large. Once we get to 100 out of 150, we have passed the point of more than half of that carrying capacity, and so our rate of increase is going to slow down. By the time we reach our carrying capacity, so when we are at, say, 149 out of 150 individuals, we get down to a rate of increase where we're at 0.02, and so that rate of increase slows when there's not enough resources to make more babies or to feed everybody in the population. There's not enough nest sites, things like that. So as your population size approaches the carrying capacity, the rate of population growth, which is your dNdt, decreases to 0, so that the more of the carrying capacity that you are using, the slower the rate of growth. So because logistic growth is the more realistic type of population growth, and it's the type that most populations of living things are undergoing, it's important to know the carrying capacity and the population size of different populations when we are trying to manage a population of resources, such as forests or fisheries or deer, because you want to maintain the population at a size where the rate of the population growth is maximized. So you want to know the carrying capacity as well as population size so that you can see where the curve is the most steep, where you're having the greatest rate of increase, because as your population size approaches the carrying capacity, the rate of your population growth decreases to 0. And so there would be far less turnover in that species when you're at carrying capacity compared to when you're sort of in the middle of it and you have the greatest rate of increase because you still have a lot of resources left and enough individuals to be able to keep adding to that population. In your slides, there's also a link to a model for logistic growth. And so you can play around with this in the same way that you did with exponential growth and look at the way that different factors such as the number of individuals in the population, the rate of increase, carrying capacity, and things like that are able to influence your population size and your growth rate. So I encourage you to use this as well and look at how those different factors can change things in your population. When we're talking about things that can regulate the size of a population, there are two different groups of factors that affect population size. There are density-dependent factors and density-independent factors. Density-dependent factors are going to have a stronger influence on the population as the population size increases. So having more individuals makes these factors act stronger on that population. So an example would be predation, where if you have a larger population size, you're easier to find, and therefore predators are going to prey on you more than something that's rare and hard to find. Competition works in the same way, where if you have more individuals, there's more competition for resources, and that's both within a species and between different species. And so as your number of individuals in your population increases, the competition for resources, so for food and space and water and things like that, is stronger. And so the larger your population, the greater your competition is. Also things like parasites and diseases, where a larger population size will generally mean that those individuals are packed in a little bit closer together. And so the spread of parasites and diseases is a little bit easier and happens more in a dense population than in a more spread out population. So if we think about, for example, the coronavirus that's happening right now, at the beginning of the coronavirus, we saw a very rapid spike in the numbers in New York City, which has people that are living very close together and using a lot of the same stairwells and elevators and the subway system and things like that. And they're in very close contact. And so that disease was able to spread a lot faster than in places that are more rural, like in Nebraska and Oklahoma and Kansas and things like that, or even Montana. And even Phoenix, where people are a little bit more spread out. So the denser the population, the greater the spread of that disease. There's also an issue of the amount of toxins and waste buildup when you have a denser population. So it's kind of gross to think about, but an average person produces 1 pound of fecal waste every day. So if you have a city with 5 million people in it, you have 5 million pounds of fecal waste that you have to figure out what to do with on a daily basis. And so making sure that you have good management for water services and making sure that you're able to keep clean water supply is an important factor as your population gets bigger. Factors that are density independent are things that regulate population size, and it's not related to the size of the population. So this would be things like natural weather events, so weather events that are not caused by climate change. At this point, most weather events are impacted by climate change, so the number and size and strength of hurricanes is getting larger as the population size grows larger because of climate change and things like that. But a better example would be something like a natural disaster, such as like a volcanic eruption or something like that, where the that volcano erupting could kill a lot of living things around it, but that's not, the volcano's not erupting because of the size of the population, and it's not going to kill more people simply because there's more people on the planet. It's going to kill more people if more people, or birds or trees or whatever it is live near that volcano. And so that would be density independent. The volcano is not caused by population size. It simply affects anything that is near it. In a lot of populations, especially predator-prey populations, we see population cycles where there are some organisms that have populations that show regular boom and bust cycles, where you have a cycling dynamic where the numbers increase and then decrease. And the classic example that is usually used for this is of the Canadian lynx and the snowshoe hare. And we can look back at the number of individuals that were trapped in those areas. And we have data all the way back into the 1840s. And so you might be thinking, wow, who was taking data on this back then? Well, it's actually people who were killing these different animals for their pelts for the fur trade. And they would keep track of how many of each animal they were killing in any given year for their pelts. And so we have good data on this very far back. And if we look at the population cycles of this predator and its prey, we can see how they fluctuate over time. So in this case, we have a lynx and a hare, and this is how it would work. So you have a bunch of lynx in a population and they're hungry. And so they're going to hunt the hares. And so if you have a lot of lynx, they're going to eat a lot of hares. The hare population drops, and then the lynx population follows because now they don't have enough food source to keep them alive. Once the lynx numbers go down, the number of hares can then increase. Once the number of hares increase, the lynx have more food, they can prey more upon those lynx, eat more, have more babies, and so the lynx numbers go up. The lynx numbers go up, that causes them to hunt more, they kill more hares, hare numbers go down, and the lynx follow. And so if you look at this chart, you can kind of see that their numbers don't increase at exactly the same time. There's an increase in the prey, which is the hare, first, and then an increase in the lynx following it after the number of the prey have increased. Population growth rates are also related to life history strategies. So we talked in the last lecture about life history strategies, and we talked about R-selected and K-selected species. So K-selected species are adapted to stable environments, and these would be things that we would see a logistic growth rate in, where the population is usually going to be close to the carrying capacity. These individuals typically have a type 1 survivorship curve where they are providing parental care, they are long-lived, they don't start reproducing until later in life, and so they'll have a few offspring that are well fortified and that they take care of, and instead of having a lot of offspring. The other type was the R-selected species, and these types of species are adapted to unpredictable or unstable environments. And the benefit of that is that if you have an environment that will sometimes have a lot of resources and sometimes have fewer, if you are selected, you can have a lot of offspring. And if it happens to be a good year, you're producing a ton of offspring that can utilize all of those resources in that good year. And therefore the numbers will go up. On a bad year, more of the offspring will die than survive, and you end up with lower population numbers. So these species that are selected will go through boom and bust cycles, where in good years they'll have a lot of individuals, and in bad years they'll have fewer. And they typically have that type 3 survivorship curve where they have a lot of offspring in the hopes that it will be a good year, and most of the time, most of those offspring end up not surviving. But they're having a ton of small offspring that can survive on their own and don't need parental care. And so they're using a numbers game where they can use resources in a good year, but they're never going to be a stable population that sort of rests at their carrying capacity.